Uh, Here we will have a understanding of the induction motor equivalent circuit. Induction motor, you know that it has got a stator, and inside it there is a rotor. So if I have the input power is given by PIN, there are okay, this is a stator end. Some power is lost in the stator resistance. Then there is a rotor. So the power is whatever the PIN is there, some power is lost, and whatever the power which is between the stator and the rotor, that is the air gap power PG. Now the rotor is having a copper loss. The power which is there in the rotor will be like from the rotor, output of the rotor will have a mechanical power PM. So these are the three powers, and from the mechanical power, if we subtract the friction and windage loss, we will get the soft power. We'll just connect it output and we'll get the soft power PSH. So we are basically deal with this PM mechanical power and air gap power PG. Now as we discussed that there is a resistance on the stator. So stator is obviously having a resistance RS, and the flux which is there, this flux usually links between the coils like this. It is like within the stator and himself, though these fluxes are the leakage flux, and these leakage flux actually leads to the leakage reactance. So we can have XS as a leakage reactance, and there is another flux is there which is also there between the stator and the rotor, that is called mutual flux phi m. I will come to it a little bit later. So then we come to the rotor side. The rotor is also having a resistance. So this resistance is called RR, and rotor is also having a leakage reactance, and this reactance is called XR. And we may talk that this is on the rotor side, like this is the rotor side and this is on the stator side. They are the two separated, and just like a transformer, primary and secondary, they may have a equal turn ratio or they may have a different turn ratio, and usually the input is three phase, right? So what we are writing is we are just writing RS and XS. This is the per phase quantity. So all the rotor side and the stator side, these are the per phase quantity. And if we mention the input voltage as V1, or I can say input voltage as VIN, and the most suitable way of writing is input voltage as V1, and the voltage which is induced in the stator is E1, and voltage which is induced in the rotor is E2. So we can have like a transformer type of thing. We are saying V1 is the input, E1 is the voltage induced in the stator, E2 is the voltage induced in the rotor, and finally whatever the load is there, that is output voltage is V2. We can have this significance will be there. In this way we can proceed. So now if this rotor parameters are referred to the stator one, so obviously we'll put a dash over here, RR dash and XR dash. On the stator side, let us say what is the supply is V1, and you have got E1 is the EMF induced in the stator winding here over EMF induced in stator winding. And as we talked about, there is a mutual flux is there between the stator and rotor. These mutual flux can be represented by a parallel coil. We can also represent, just like in transformer, one resistance over here which is in parallel with the mutual inductance XM, but we can neglect it assuming that this is very high, or the other side XM is low compared to the resistance, so we can neglect that resistance part. So instead of adding a resistance over here, we will just neglect that, and we will only keep the XM over here, magnetizing reactance. So flux is there whenever there is a flux. So flux can be represented in terms of L, N phi by I, and L can be multiplied with omega to write X. So this is actually, we can write how we can write that. That means if we have a flux anywhere, we have a flux multiplied with n number of turns the flux linkage divided by the current, which will give rise to phi n by I, give rise to L. And if I multiply omega with L, that give rise to X. So anywhere if there is a flux, I can relate that flux in terms of magnetizing in flux in terms of X, in terms of reactance. So there is a one term called leakage reactance for the stator, reactance for the rotor, mutual flux, and that leads to the mutual reactance XM. So in this way we can relate all the terms. And now in the secondary, so this primary side is okay, this primary side is enough, this is fine. But the secondary side, we need to do some homework over here. So let us redraw again. In the secondary side, what happened? We have a voltage E2, and here we have the resistance R2 dash refer to the primary side, and we have got a reactance X2, or let me write in that, we can write as RR dash XR dash as per rotor. And let me short circuit this. Now out of these three terms, there are terms like E2, EMF induced in the rotor. The EMF that is induced in the rotor over here is actually E is equal to N d phi by dt. So the rate of change of flux actually determine the EMF induced, the frequency of the EMF induced. So if my supply frequency is Fs, so the flux is running at a speed of 120 F by P, 120 Fs by P, and because of that flux, the EMF whatever is induced, its frequency is also Fs. But what happened, because of the Lenge's law, the rotor start rotating in the same direction of the flux, and the relative speed between the stator and the rotor decreases. If the relative speed will decrease, so obviously the frequency of induced EMF will decrease, and that lead to one answer is that we have to multiply here S, the term called slip, where the slip is nothing but ns minus nr by ns, or I can say the slip correspond to the relative speed. What is the difference between the stator flux and the rotor? So this value will actually, s is multiplied with the frequency. The earlier whatever the frequency is, the 50 hertz. Now because the rotor start rotating in the direction of the stator flux, so the resultant frequency will low, as the emf induced will also multiply by the s. Similarly, the reactance also here s is multiplied, so we have got these two terms where s is multiplied. Now the circuit is complete. So can I redraw the same circuit over here? Like because this part of the circuit, can we redraw this circuit like this? That let me write that in the, if this is a pitch situation, what is the value of I2? So I2 is nothing but S E2 by RR dash plus JS times of XR dash. Right. So can I write this I2 expression again? The I2 is equal to EA2 by RR dash by S plus XR dash J. We can write that, right? We can change this. So if we can change that, the equivalent circuit will now look like that. We have a input voltage as E2. Now we have got a reactance X2 which is free from S, and a resistance term is there which is now given as R. Okay, I'm writing here as parameter. Sorry. As XR and RR by S. So with the delta term. So in this way we can have the same expression, but now we have got this is free from S and this is free from S, and this is a term which is there divided by S. So it is actually, this makes the resistance variable. Now we can have we can say the resistance is a variable resistance. So this type of equivalent circuit give me a flexibility to redraw and attach with the equivalent circuit of the primary winding. So here, since E1 is equal to E2, we can write, and what we can do is we can adjoin these two. And here instead of RR, we can write RR by S, and we can complete the circuit like this and representing this RR by variable point. So let me just take this thing here, copy this thing from here, copy this thing from this one, and place it over here. Right, so now this equivalent circuit, let me try to redraw again. Now this equivalent circuit we will redraw again here. So this is one of the equivalent circuits, so let me just redraw it again. So now we have this side as resistance RS, then we have leakage reactance XS, then I have a magnetizing reactance XM, then we have here now what is happening is this RR by S, can I split that into RR plus RR by S minus RR? So that give me like adding one RR and subtracting one RR, and this will give you as RR plus RR 1 by S minus 1. So here what is the advantage is that we are writing here as RR dash, and then we are writing here with XR dash, and this RR extra term, this term we have added here, and like this term we have added over here, and this term we will be adding over here. So for that we can redraw this and represent this as variable 1 and saying that this is r dash 1 by s minus 1, and this our equivalent circuit is complete. And here we have mentioned here as v1. This one is e1, which is, we can say e1 is equal to e2, and here we have the voltage v2 which represents the load end. And next we can have the current which is there, which is going to the load, is I2, and since it is representing the primary side I2 dash, the current which is going to the magnetizing is Im, the current which is supply is Is. Now we have the equivalent circuit of the transformer of the three-phase induction motor. This is a per phase equivalent circuit is ready. The per phase equivalent circuit is ready, where all the quantities here starting from V1, everything is per phase quantity, resistance, reactance, all these things are the per phase quantities. So three phase, it will be like 3 times of it, or root 3 vi cos phi, or we can say power is P1, so 3 phase it is 3 times of P1. So like that we can deal with it. So that is the equivalent circuit of a 3-phase induction motor. Thank you very much. In the another video we will derive the other torque expression.